Okay, so this is 1539, and this is kind of a cool problem because it combines both the conservation of momentum and the conservation of energy into one single problem. So we have a situation where a 2 gram bullet comes in contact with a piece of wood that is initially at rest, and it becomes embedded in the wood, and then the wood, some of that energy is then translated to the wood as it becomes embedded, and it swings upwards to an angle of 6 degrees. All of that swings up to 6 degrees before it falls back down. And the wooden block is 4 kilograms, and we're looking to find the initial speed of the bullet right before it comes in contact with the wood. All right, so to do this, I've laid out kind of 3 states. All right, state 1 is prior to the bullet striking the wood. Uh, so this is the first initial velocity that we're trying to find. And then immediately after the bullet becomes embedded in the wood, so it hasn't changed height or anything yet, it just the bullet becomes embedded in the wood. And lastly, state 3, and state 3 is the time when it swings all the way up to the top 6 degrees and comes to a stop before it swings back down. So those are the 3 states here. So let's write our first conservation of momentum equation. So we have m1v1 equals m2v2. So this is prior to the bullet striking the wood and right after the bullet strikes the wood. So this is the mass of the bullet times the v1, that's the velocity that we're trying to find, and mass 2 is right after it becomes embedded, the mass is the mass of the bullet plus the mass of the block. And that is v times v2. And we don't know v1 or v2 in this equation, and that's where we need to go into our conservation of energy equation. Okay, so our conservation of energy equation, we have the kinetic energy at time 2 plus the potential energy at state 2 equals the kinetic energy at state 3 plus the potential energy at state 3. Now, at state 2, we're going to call that at 0 potential energy. So that's right when the bullet becomes embedded. This thing hasn't started to swing up yet. So we're going to call the potential energy at that state 0. And then state 3, after it swings all the way up to 6 degrees there, it comes to rest. So the kinetic energy at state 3 is 0. So we just have T2 equals V3 here. And T2 will come out to be 1/2 the mass of the bullet, because this is right after it becomes embedded, plus the mass of the block times V2 squared. And the right-hand side is going to be mgh, and m is the mass of the bullet plus the mass of the block. G is obviously 9.81, and h is really the maybe tricky thing that we need to find. So h is actually the distance that it changes in height from the bullet first striking to when it becomes a velocity of 0. So that small height there is what we're looking for, is h. So what is that distance? Well, let me draw a triangle here and see if we can. So initially, the cable that holds the block is 1.25 meters long. Okay. And then after the bullet hits it, it swings upward, but the cable length doesn't change. All right. So I'm going to draw this something like this. All right. And the cable length is still 1.25 meters long. All right. And we know from here to here, 1.25. And the height change, let's see if I can draw this. H is the distance here to here. So that is h. All right, and we have this being theta. Theta is here. So what is this distance then? X. Because we know h is going to be equal to 1.25 minus this distance x, right? That's h. So 1.25 minus x should equal h. Well, h is or x is nothing more than 1.25 cosine of theta, and that should be the projection of that. So this is 1.25 cosine of theta there, okay? And theta is 6 degrees, okay? So filling out this equation, it comes out to be 1/2 times 4.002 v2 squared equals 4.002 times 9.81 times 1.25 minus 1.25 cosine 6 degrees. All right, and solving for V2, let's see where that's at. V2 comes out to be 0.3665 meters per second. Now we can go back and look at our conservation of momentum equation, this equation here. So we have just solved for V2 here, and now we're solving for V1. Let's do that. So we have the mass of the bullet, 0.002 times V1 equals the mass of the bullet plus the mass of the block, 4.002 times V2, which we just found out is 0.3665. And then V1 comes out to be 733 meters per second. And that is the solution to 1539.